Okay, we start up. It's not the best room, but it works. Now, for most of the rest of the semester, on Thursdays, I have booked shell number 4, which is then just the other room here. A little bit better, a little bit bigger. Bigger screen, I think. But on Wednesdays, we are stuck with our lunchroom, so but I'll put out the information here on It's Learning. What you also now find on It's Learning is the videos from last time. So I'm going to publish them continuously like this. So there you have the links for the different hours, and then short description what it is. It should be click and play here. So the quality.
Start up.
Oh, shut up. Quality shouldn't be too bad. A little flickering here, but I think that's unavoidable. Should be possible to read what I write on the blackboard. If I had a better handwriting. Okay, so they should be there, and I will continue to list them. What I also gave you is an exercise. I was going to put out the startup of the Poiseuille flow, as I showed you last time, put out the MATLAB files here, but then I thought, hey, that was a really good exercise for you guys. So I put out the MATLAB scripts. The only thing you need to run the code, but I have removed the one I showed you, the solution from the FTCS scheme. So here you'll now have an exercise. You have been given the problem. Here actually is written already on the non-dimensional form, but you should go through the entire step to obtain this equation from the Navier-Stokes cylindrical coordinates with dimension, so that you can see how it's done. You're going to need that also because as a driving force in the system, you have a constant parameter k, which here I've set to 0. It has to have a value, and it has to have a certain value if you want the maximum velocity to be 1 at as time goes to infinity. So here you'll have several steps that you would need to do. Find an FTCS scheme, making the double derivative, single derivative, finding a position r also enters into the equation system. And then the boundary conditions, where you are on the solid wall inside the pipe. That's not a problem. Velocity should be 0, no slip condition. Problem is the center line. There you have the derivative equal to 0, meaning a Neumann condition. How to program that one into your equation system? That can be a little tricky. Initial conditions, everything equal to 0. So if you run this code now, you see you only get the Szymanski solution, the analytical solution. So your job for this exercise, get it correct. So now the velocity is just a 0, it's just a blue line here. So that is exercise 1. Now I don't have ordinary exercises in this course, so I just give it out as a voluntarily exercise, just in case you are getting bored this weekend. Now you have something to do, play around with it. And of course I'll provide you with a solution later. So don't hand in any exercise answers. I'm not going to look at them. I'm not going to correct them. Okay. Any administrative questions while we're here? That's okay. So for the rest of the semester, Wednesdays in the lunchroom, And then the time should roughly be 8:30, 11:30. Due to the 11:30, it's lunch. But on Thursdays, we will be mostly in Kjell number 4. I got it for most weeks. A couple of exceptions where I have to find another room or even use the lunchroom again. I'll see. But I'll put out the information here on East Learning, so just pay attention here. Okay. Last time we stopped at the projection method, time split method, how to solve the Navier-Stokes using a Poisson equation for the pressure. And there, as then said, that's the Poisson equation for the pressure that is expensive. That's where we have to set in our efforts. So what we are looking at now, solving a Poisson equation or a Laplace equation, really just the same amount of work. So solving equations that is elliptic equations, if you can recall, then you need boundary conditions all around to find a unique solution. How to find a solution? Well, we are going here to use an iterative scheme based on Newton-Raphson's method, finding here a 0 point for a general function. So this is the classical recipe, actually invented by Newton, so it's fairly smart. You have a continuous function f. Find where this function is 0. Okay, you start guessing. You give him an argument, here an s, and then see what you get. You get something different from 0. Okay, at the point you found, find also the derivative at that point. And then you continue with this gradient all the way down until you cross the s-axis. And then you have a better guess, hopefully. Then you try with this one and do it the same once more, finding the derivative here, prolonging the line until you again find another one. And so you continue all the way down until you are satisfied. So it's a very simple, straightforward method. And you find the recipe for it from Taylor's theorem. Taylor series, Taylor's expansion for the function f around a point s. So your recipe then, your iterative recipe stands here. An initial guess, then you find an adjustment, and you get a better guess. And so here you continue from n equals 1 to n equals how many you want. Could be a very big number. Now this was for finding where the function f is 0. That's not our problem. We need a function that can vary with more than just 1. So we modify it. Our equation is a function of many variables. And our equation is just an algebraic equation, of course, is coming from this one. So from your numerical scheme, you will have an algebraic equation. Here I've used different u as the unknowns. Like you have a recipe ui plus 1 to ui plus ui minus 1 divided by delta x square. This is actually u double derivative, for instance. Saying this one is equal to 0 or something. Okay, then you have your function, your f function here. Since I have 0, I can multiply with delta x. So this is actually now my f function, only with 3 arguments. So what will my stencil be here? Well, the updated value, the one you are focusing on, could be either of these three actually, but it's always smart to pick the one in the center. It will be more stable, it will be faster. You could have picked either one of these three and said, I want to find, say, him. Yes, you could do that, but much smarter to take the one in center. So here I will now write an iterative scheme saying ui, he will be based on the old value, and then minus this f function divided by the derivative of this f function with respect to the unknown that I picked out, the one I want to have the focus on. So the derivative of this one with respect to ui, well, that's just minus 2. So that's it. So yeah, there you have now the recipe. So you have to do this many, many times for all i's, and then for many, many iterations. Hopefully then he should tend towards the correct solution. This is sort of the basic for the modified Newton-Raphson. To speed up things a little bit, you can invent sort of an overdo it parameter. You might say that this is your old unknown, this is the adjustment we have calculated, hopefully to get him to be more correct. If you sort of exaggerate this adjustment with a number bigger than 1, then you sort of go a little bit too far every time. The philosophy is actually not so stupid. You can see here. Here I have my guess Sn, and here the recipe says here should be the next one. So this will now be a delta quantity, and then we take this delta and multiply with 1.5 or something, this omega number. Then we might be lucky and find a solution faster. And yes, and it actually works. So in general, this omega, he should then be between 1 and 2. The closer to 2, the better, normally, depending on how many unknowns you have. So he can be a function of many, many parameters. How many unknowns do you have? How big is the problem? The equation system itself. It can be very hard to find the smartest, the optimum omega. So here you just play around with some numbers and see how which one is fairly decent efficient, or most efficient. When you do this programming here, this very simple equation system, typically what you would do, you have u, which then is in MATLAB zeros of 10 by 10 or something like that, if you have a two-dimensional problem, for instance. Everything is equal to 0, and then you are going to use this recipe. So you will have something like this for I equals maybe from 2 to 8. If number 1, no, not 8, 9. If number 1 and number 10, they are on the boundary. They are then used for boundary values. More of that later. So this one now should be the internal field in the x direction, and here for j equals 2 to 9 in the y direction, and then I would write u of I comma j equals the old value, and then minus minus should be a plus. So I will write something like this, plus omega half, and then the entire f function here, ui comma j minus 2u, no, sorry, I plus 1 comma j, u I comma j plus ui minus 1j. Something like that. and so that's just an example for 1D, just a derivative in the x direction only. If you program it like this, what do? You overwrite your arrays all the time. So you don't store your calculations. You use just one single array all the time. Meaning, for this double loop here, where you sweep across the entire domain, some of the values will be just updated. Some will be from the previous iterations. Because you are going to need an outer loop here for iteration equals 1 to how many iterations you're going to need. So you have to do this many times. So now the question is, how should you program it? If you do it like this, you overwrite your values all the time, then you call it Gauss-Seidel iteration. And if you program it without thinking, that's what you would do. You just overwrite them. While if I demand I will only use old values, then I have to create some additional storage. I can't use the same name here. Then I must call him something else. Call him new u or something like that. Then it will be okay. Now he will be based on only values from the previous iteration. And then after I have done say for I and for j here, I would then write something like this: u equals new u, and then continue to the next iteration. Now it is Jacobi program. You see the difference? Why is that so important? Well, we will see later when we try this using an omega, an over-relaxation parameter to speed up things. It has to be Gauss-Seidel. If you try that with Jacobi, it's going to blow up. Trust me. So when this omega is bigger than 1, meaning you have to program it with Gauss-Seidel, not like this. You have to use the updated values all the time. And then omega bigger than 1, then we call it an SOR, successive over-relaxation. As a test case, very simple. Double derivative equal to 0 in both directions. Any questions to this one? That's okay. What is my problem here? So double derivative of the temperature, just to have some physics connected to it, should be equal to 0, a Laplace equation. And then I mix my problem a little bit. I have a square area in space. I have a cold right wall. Temperature is 0. Then I have a hot ceiling. Temperature is 1. And then I use Neumann conditions for these two walls, meaning they might be insulated or something. So that is my problem. A mix of Dirichlet and Neumann conditions. The equation, writing this one out in two dimensions, will read something like this. Central differencing, second order accurate. So here you will have the y direction, j plus 1 minus 2 center point plus j minus 1 divided by delta y square. Same in the x direction, then it's I plus 1 and I minus 1. Now for simplicity, use the same number of cells in each direction, so the deltas are equal, using just an h instead, and rewrite the equation system. You get something like this. When you have 0 on the other side, of course, h square and h square can be cancelled out. So my f function that enters into the recipe for the modified Newton-Raphson now looks something like this. You have 4 points you are focusing on. And if you look at now, say, an arbitrary line I and an arbitrary line J, then you are focusing on the unknown point here. This is my Tij, the center point that I'm looking at. To create double derivatives, you use neighbor points in x direction and you use neighbor points in the y direction. So here you will now have what we call also a discretization star scheme for your algebraic equation, only using the closest neighbors. You could have used more neighbors if you want, say, higher order method. This is second order accurate. If you want fourth order, eighth order, then you're going to need more neighbors normally. So we write it on the form now. Our function equal to 0. If you have the correct values here, yes, it's going to be 0. Then we have solved the numerical version of this one. And here it should be possible to get it fairly close to 0. Inserting now for the modified Newton-Raphson method, my new center point value equals the old one, and then the adjustment, which we are going to enhance a little bit. The derivative, well, that's just -4. So no problem there. So here now is my recipe for an iterative process, finding better values, hopefully. Now, this is only the internal part. We have the domain like this, a square in x and y. So the problem is now the wall values and the corner values here. How are we going to deal with these? For the internal points, there we have the recipe. That's not a problem. And they may address the temperatures here on the walls. Yes, that's true. But there were only 2 walls that were where we had constant values. We had this one as 0, and this one we're given as 1. The corner point here will be a question, but he's not going to be used. You can tell from the star, discretization star, this one is never going to be addressed anyway. So here, I just one single unknown. He's only using these values. So this one is never addressed, so you can give him any value you like. For cosmetic reasons, I think I gave him 1/2 when we are plotting this. So these boundaries with Dirichlet conditions, that is not a problem. You just give them the values directly. What about these walls? There we have to do something. So here I say I want to know the temperature on the wall itself. So that's my first unknown point. I want to know what the temperature is here. The boundary condition says derivative equal to 0. Okay, then I need a derivative at that point. Here I could have taken a forward difference, saying I want a derivative, so I use the unknown point and the right neighbor. I could have done that. It's not so nice because that's only first order accurate. if you think in terms of central differencing, then you actually calculated the derivative in the midpoint between those two. So instead, what I'm going to do is to use a ghost cell inside the wall, a fixture cell, and say the derivative on the wall now will be difference between these 2 points. So this one cell inside the wall. He doesn't exist, but I use him anyway for creating this derivative at that point. And I know the derivative should be 0. Okay, then you set up first order derivative around point 1. Okay, these two then just has to be equal. So you just invent something here that's equal to whatever value you have inside the domain for the cell closest to the wall. And then you will get your special version of the recipe, the iterative scheme here. You see for I equals, well, it should be 1 here, not 0, because these are still my unknowns. I have to find them, I have to calculate them. But they are, in general, now going to be based on a value inside the wall, which I don't have. But I know he's equal to this guy, so you see the recipe here. You get 2 times of the one that you have inside. That's the only trick. And the same, of course, in the bottom wall. That was the derivative in the y direction equal to 0. Then you use a fixture cell down here in the same manner. The problem here has an analytical solution, so it's possible here actually to check how it works. But we could have compared with that one, but it's easier actually to see it. So let's try it. So here I have a cute little code. This one I will put out for you. You don't have to do this as an exercise. I have 100 unknowns in each direction. So it's a 100 by 100 problem. Actually not so big. The omega, I start with 1. And my unknowns, zeros of n, so it's 100 by 100. Then I provide him here with the boundary conditions. So at the top, the right wall is 0, top wall is 1. And then this strange corner point, I just give him the value 1/2. And then we plot the surface. Then comes my iteration loop. So how many iterations you are going to need, you don't know, you just have to try. But what you can do, remember this function Fij, which was equal to your entire algebraic equation written on the form equal to 0. So then you just check, is it equal to 0 or not? So there, this one will sort of be a residual, an error, which we then use to adjust our solutions all the time. So that's another way to think about it. So I start here. I say my error is 0. And then I go through the entire domain, the entire internal points. Careful here, I start with 2. I don't take the first one, because there I had a special version. But then I update my unknowns directly according to the recipe. So that's just one sentence. Here I actually do the calculation once more. I sort of accumulate the absolute value of this error and just see what he becomes in the end when I have done one iteration for the entire field. So that's one way to check if your solution is, if your approximative solution is getting closer to what it should be. Then here I need a couple of extra loops just for dealing with the two walls. They had a special version of the recipe. And finally, I have one very special version. That's the unknown corner point here, because he uses actually this one and this one as well. So he needs special treatment. But that's all. So now let's try this and see if it runs. Here you have the initial state. So x and y, that's sort of the bottom here, the temperature. And it was 1 for the top wall here. Temperature is 1, and here it is 0, and initially 0. And then we start to iterate. And yes, it actually seems to be working. He doesn't update the adder. That was too bad. Why doesn't he do that? Let's try if we can find that one. That was strange. Yeah, I start with setting it to 0 here, but then I accumulate it up, and I thought I plotted it here. So there he should have a value. Shouldn't be 0 there, shouldn't he?
You should put 0 outside the loop.
Maybe it's because it's an integer, and it should be.
No, it's not integer. Here is numerics to string. You have the other one that's int to string. So it's a real number. Very strange. Just want to check it. No, he's 0 all the time. How come? Amazing. He says we have found the solution.
When you put 0, it should be 0 point dot to the area.
Oh, here you mean? No, that's not MATLAB. He doesn't care whether you do it like that or... No, that doesn't matter. So, okay, let's...
Put it outside the loop? Like outside the iteration loop?
No, I want to have it updated for every iteration.
Yeah, no, but I mean the 0, the Fij equals 0.
No, because you start with setting him to 0 when you begin one iteration. And then you accumulate up, and then finally, what is f for this iteration? So why doesn't he want to accumulate it? Is he just lazy or what?
Every time you do the iteration, you will reset the f equals to 0. It won't accumulate that.
Nah, he should. This is going to be crazy, but I want to see this. He's 0 no matter what we do. I think I know. Yeah, of course. That wasn't so easy to see. I mean, I have just updated the Tij here so that this equation is fulfilled. So of course it is 0. I have to do it like this. Then actually I get the outer from the previous iteration, but who cares? Yeah, that helps. Remove the printout, and we run again. So here the problem is, the method is slow. The solution will be symmetric around from this point to the other corner. This point here, that is this special corner point, should be of course symmetric around this line here. So the temperature here should be 1/2. And after 500 iterations, he hasn't even started moving the anode, fairly big. So no, this is going to take forever. You could have continued more zeros, thousands, 10,000s of iterations. Yes, that's possible, but it's going to take forever. And here, you might argue that choosing 0 is a very stupid initial guess. So if you now say the initial value should be 1/2, I start with that one instead. That should be closer to the correct answer, yes. Still, it takes forever. I mean, this point is now fairly okay, but to get the entire solution correct, he's very slow, and not much change from one step to the next. So he's getting there, much smarter than just starting with 0, but still no, not good. Say if we do another initial field, here I used a random generator, random numbers between 0 and 1. Not so smart either. It's the same problem more or less, like we had the last time. So that doesn't speed up things either. Now let's try this omega trick. Omega should be a number between 1 and 2. So let's try 1.5. And I go back to the initial 0 solution. So now see what happens. That didn't help much. Maybe a little bit. Let's try a bigger omega then. 2. Omega 2. Okay, now we are getting some action. But it doesn't look too promising, does it? No. So the anode, very big indeed. And here, if you now try 2.01, just a little bit above 2, he's going to explode. So 2 is the absolute limit, as you can see. Nice colors though. So we can't use 2. But here, actually, a number very close to 2 is a very good idea. 1.98. Sort of you take a rug and you shake it. So there you see he finds the solution much faster. Here now, very small anode, and the field quite symmetric and nice, as it should be. I could have compared here with the analytical solution, but trust me, this one is quite nice. While we're here, I wanted to give you an illustration. Yeah, any questions, by the way, so far? That's okay. I've done this several times already, and I have punched here in the anode after 500 iterations, trying with different values of this omega. So if I now plot x versus y, you get this plot here. So here, the x-axis, that's different omega values. And the anode, after 500 iterations, is the y-axis. So the smallest anode we find down here, 1.97, 1.98. So to get this graph, okay, you had to do it many, many times. There exists a numerical theory that can find this optimum omega for you. For a linear equation system, then this one is sort of the cutest one you can find. Then yes, it's possible to find it fairly easy. More complex equations, I said don't bother. You're going to spend more CPU finding an optimum omega than actually solving the problem. So just play around with the omega. You don't have to do it many, many times before you find a decent value that can speed up the process. But let's go back to the case where I started with the random generator. And now omega 1.98, the optimum omega. Initial field. That wasn't my intention. One more. Busy. Like that. So a big omega or an optimum omega, he sort of have a balance here between this high frequent noise versus the low frequent behavior of my solution. If I now go back to omega equals 1 that I showed you, initial field, you see what happens very rapidly. All this high frequent noise disappears. It's smeared out. And then you are left with now a very low frequent anode, which the algorithm takes forever to get rid of. You can see it better if I take a pause for each iteration here. Initial field, and now one iteration. You see a lot of this noise has been damped quite substantially. One more, two more, three more, 5, 6, 7, 8. Now things are sort of smoothed out a lot, and from here on he doesn't do much from one iteration to the next. So he was very efficient in the beginning. Now he is outdated. You see, he doesn't do much from one step to the next. Nothing much happens. This property for this classical Gauss-Seidel and also Jacobi iteration, that is the basis for multigrid methods. If you want a solution fast, you start with this on a fine mesh, the finest mesh, the one that I have here. You start like that, and then you do a couple of iterations, not that many. Actually, in practice, 2, 3, that's enough. And then you'll have a solution that now is now quite low frequent. Low frequent. Then you transfer this problem over to a mesh which has only half the number of cells in each direction. Then this wavy pattern will appear more high frequent. And then you do the same there. A couple of iterations there as well with this old-fashioned method, the classical Jacobi Gauss-Seidel with omega equals 1. And so you can continue even on even coarser grid. Sooner or later you have to go back again, of course, to adjust the fine mesh solution, but that is actually quite so efficient, and it's actually the most efficient method available for solving n equations. It can solve it with order n operation. So multigrid, very, very fast indeed. And optimum omega, that would be terrible because you see here now omega 1.98, 1 iteration, 2 iteration, 3, 4. He sort of keeps the high frequent noise alive. He still actually is doing something sensible. Not so easy to see that he has done anything sensible at all, but actually he has. But he does it sort of from the two phases where we have a constant temperature, and then the solution will spread out more into the inner domain. So yes, omega 1.98 here is much faster in the end to find a good solution, yes, but not with respect to removing high frequent noise. So he will be terrible to be used in multigrid. But here and now, yes, that's the best choice for finding a solution fast, obviously. Before we begin, let us try the difference here between Jacobi and Gauss-Seidel. Now it is programmed as a Gauss-Seidel iteration. You see I have the equation here, Tij equals Tij, meaning I overwrite. Let's not do that. So before I start here, I have copied my entire temperature field to a new temperature. Then I just reprogram here a little bit. New temperature. And the same here, new temperature, and also here, and finally the corner point, like that. Now all of them has been sort of rebaptized. I have my new temperature field. All of them are based on only old values. Okay? Then finally, of course, I have to copy that one back to the temperature field. T equals the new T, like that. So now let's run this one. We can start with random, that's okay. Omega is now 1. Well, he's also fairly decent in filtering out the noise, the high frequent noise, but a little bit different, isn't he? Let's remove this stop button, should be here somewhere, like that. We can start with without this random, like that. Initial field, and then we I'm not supposed to do that. Why does he? Of course. Thank you. Now it is Jacobi instead of Gauss-Seidel. Omega is 1, and you see it takes forever, and he is not faster than the Gauss-Seidel version. Actually, he's a little bit slower, so this is a bad idea. You shouldn't do it. Now we try to increase the omega. 1.1. See if that helps. No, it doesn't. You can't do it. If you want to use an over-relaxation and omega bigger than 1, you have to program it as Gauss-Seidel. You cannot program it as Jacobi. It will be unstable no matter what you do. Strangely enough. And here I just programmed it sort of straightforward. For I equals 2 up to n minus 1, for j equals 2 up to n minus 1, I could have programmed that one quite differently. I could have taken every other point and then the in-between points afterwards. You can do it in either way. The whole point is, you have to overwrite the unknown inside your array as you do the calculations, as you do the iterations. But how you do it, that really doesn't matter. So my point is, to be allowed to use an omega bigger than 1, it has to be Gauss-Seidel. Any questions?
But then why do we have Jacobi existing? I mean, then we can always use Gauss-Seidel.
Yeah, why do we have Jacobi? Well, I would guess the first programmer that did this, I guess he didn't even think about it. He just overwrote his arrays directly. Also, in those days, the memory was expensive. But later, we needed a name for it. And actually, we are going to use Jacobi later on when we are talking about multigrid, because Jacobi can be a little better, smoother, as we call it, removing this high-frequent noise than Jacobi. Still, we should differ between them. Also, when it comes to stability, looking at the analysis, we need to differ between those two. But it's a good argument. I sort of agree with you. Why waste time? Other questions?
Yeah, what language are you using? Compiler to run this example that you...
If you want to run it fast, you mean?
Well, I also wonder if it's on MATLAB, but which one is it that you are using?
The MATLAB version? It's the last one, latest one, 2016, B. Yeah, but it's not compiled.
It's MATLAB, right?
It's pure MATLAB. So yes, you can do 100 by 100 here, but you need somewhat decent computer. Of course, here is just for visualization. So here 5,000 iterations, then 50 by 50 case. It's going to take forever. If you had done this program in C++ or Fortran, bam, it would be finished already. MATLAB is very slow, of course. But for illustrational purposes, it's very, very good. Other questions? Then we take a break.